Welcome to the CopperSpice YouTube channel, and thanks for joining us. In this video, we are going to continue our discussion about moving to C++ 17. More about moving to C++ 17. The release of C++ 17 contained a large number of highly anticipated changes and enhancements. Some of the new features might seem small or not that interesting. That is, until you take a closer look. Generic Lambda expressions probably should have been added sooner, but the committee had to work out the syntax. Structured bindings do not actually add new functionality, but they make it easier to write more readable code. A few of the changes we're going to look at may not necessarily feel all that useful right now. Some of these were added in C++ 17 as a precursor for new features which will be part of C++ 20. We will point these out as we go along.
Lambda expressions were first added in C++ 11, and there were major improvements added in C++ 14. One of the most important features added in C++ 14 was generic Lambda expressions. To make a Lambda expression generic, it must be declared using the auto keyword for at least one of the parameters. You may mark any number of the parameters with auto and declare others as specific data types. In our example, the first Lambda parameter is declared as generic and the second is specified as int. The compiler generates a class for both a normal Lambda and a generic Lambda expression. It also creates a method which is used to invoke the Lambda expression. With a generic Lambda, the compiler will generate the function call operator for this Lambda expression as a template. When our generic Lambda is called, two parameters must be supplied. As per the declaration, the first parameter can technically be any data type. However, for this example to compile, it must be some type which can be added to an int. Since we are not specifying the return type of the Lambda body, it will be deduced and most likely be the same as the data type for var1. As a reminder, the auto keyword highlighted in yellow is not what makes this expression a generic Lambda. This is the data type of the Lambda expression itself and should always be auto, even for a normal Lambda expression. In C++ 17, Constexpr functions have become more powerful and useful. To use Constexpr functions, it's very important to understand what is meant by the term literal type. There are several constraints a given class needs to satisfy in order to be a literal data type. As of C++ 17, it must have a trivial destructor and a constructor which can be called at compile time. These two constraints are equivalent to saying the class cannot allocate any memory during construction. Literal data types are the only types which can be used in Constexpr functions, since they can be computed at compile time. If you attempt to use a class which does not meet this requirement in a Constexpr function, you will receive a compile error. It is worth mentioning that a literal value is not the same thing as a literal data type. A literal value is simply a constant, such as the number 42.
Before C++ 17 was released, a Lambda expression could not be called at compile time. Now Lambda expressions can be Constexpr, and in fact, the compiler is required to deduce whether the Lambda expression can be called at compile time. If the capture clause and the Lambda body only use literal types, then the Lambda expression will be implicitly marked as Constexpr. You can explicitly qualify a Lambda expression with Constexpr. However, it may not be that useful. The only purpose of adding explicit qualification of Constexpr is to cause a compile error if the Lambda expression does not meet the requirements for being called at compile time. Currently in C++ 17, there may not be a lot of reasons to create a Constexpr Lambda expression. This is one of those cases where the committee added something which will be more useful in C++ 20. C++ 20 will have limited capabilities to allocate memory at compile time. This will mean that some algorithms and containers will become available for compile time usage. Then, Constexpr Lambda expressions will be more valuable. In some cases, it will be possible to supply a Constexpr Lambda expression as a predicate to a compile time algorithm, like std find if or std binary search. The example shown here works in C++ 17. It initializes a Constexpr variable with the result of invoking a Constexpr Lambda expression. Since this Lambda expression only uses literal types in its capture clause and body, it is implicitly Constexpr, even though we did not mark it with the Constexpr keyword. This means we can call the Lambda sum at compile time, and our variable named result will contain the compile time value of 15.
The structured binding syntax introduced in C++ 17 makes it easier to work with compound types, particularly when calling functions that return something like a pair or a tuple. Due to an oversight in the standardization process, structured bindings are not technically variables, and so they cannot be captured as part of a Lambda capture list. In our code, line A actually declares two structured bindings, one named X and the other named Y. Line B is a normal Lambda expression with a capture clause. In C++ 17, this line of code is ill-formed, even though GCC does not report an error. You can refer to the variable X in code following line A. You simply cannot capture it in a Lambda expression by referring to X. The workaround for this issue is to use what is called a generalized Lambda capture. Instead of the capture just saying X, you write X equals X. This is a bit silly, and starting with C++ 20, this workaround will not be required. When you define a class, but do not declare a copy constructor or copy assignment operator, the compiler will normally declare and implement these two methods for you. The compiler-generated methods are referred to as implicitly declared. The same is true of the move constructor and move assignment operator. When only one of these methods is declared in your class, the other method will still be implicitly declared by the compiler. It's unusual for a class to need a custom copy constructor, but not a custom copy assignment operator or vice versa. To prevent a potential problem, the committee decided the one implicitly declared method should be marked as deprecated. This generates a warning if the deprecated method is ever called. We strongly suggest you review the design of your classes to make sure you have explicitly declared both methods if they're needed. Alternatively, you may want to remove the one explicitly declared method and let the compiler generate both methods. Again, this advice applies to both copy and move. We would like to discuss a few other C++ 17 features you should be aware of. It was sometimes awkward to declare a variable with static storage in a header file and then need to define it in one specific source file. As of C++ 17, this is simplified by declaring the variable with the keyword inline in one header file. The range-based for feature was added in C++ 11. With C++ 17, the generalized range-based for was added, which allows the beginning and ending iterators to have different types. Since users never actually see the iterators in a range-based for, it may not be obvious when this is happening. They added this new feature because it will be very useful when ranges are added in C++20. This means that generalized range-based for loops will probably have limited usage right now. The if and switch statements also were enhanced in C++17. It is now possible to declare and initialize variables at the beginning of the if or switch condition. This can be valuable when you want to call a function and make the result of that function call available inside the body of the if statement. In our example, the variable age is initialized by the call to do thing 1 and will be in scope within the body of the if statement and also inside the else block.
The committee decided to add a new data type called std byte to represent 8-bit binary data. Prior to C++17, the char type was often used to represent this type of data. However, it implies certain assumptions. What if the data is actually a compressed file and not meaningful as a string of characters? The std byte data type will be most useful when writing classes which access raw data, like reading from a file or a socket. The register keyword was deprecated in C++11 and finally removed from the standard in C++17. If there is code in your project or a third-party library which you are using, you will need to remove the register keyword so your code will compile with C++17. The other legacy feature which was removed is the ability to pre or post, increment or decrement a bool variable. This was rarely used, so it is unlikely to be found in most source code. They removed this operation since the idea of incrementing true to get false or decrementing false to get true is a misuse of arithmetic and very misleading.
For more information about the CopperSpice project, please visit our website at www.copperspice.com.
Thanks for watching. We hope you found the content of value. If you have any questions or feedback, feel free to leave a comment on this video or send us an email.
Please make sure you subscribe to our YouTube channel and come back in a few weeks for our next video.